APEC 2024, we're in Long Beach, California. This is Martin Rowe from EE World, and we're at the Picotest booth. Steve Sandler is here and Charles Heimowitz is behind him. And what we've got over here, there's a lot of talk about 800 amps, 1,000 amps, 2,000 amps, as you can see here. And it's all the data center people. They all want it for their switches, for their servers, and it presents a problem. So Steve, who is very good at solving such problems, is going to explain to us about this board that he's got here and some of the components on it and how you do the measurements. So Steve, why don't you tell us about that?
Well, that's a nice introduction, Martin. Thanks, it's great to see you. So yeah, we have customers mostly from the data center and AI world, and their processors are getting really dense. So they've been asking us for a couple of years if we could build a device that would allow them to test their power rails ahead of the actual delivery of an ASIC. It takes a long time to develop the ASIC. And so we spent a few years designing this, and we finally came out with a solution, and we built a few versions of it. This one here you can see is using a brand new Analog Devices power module. We built a few different boards with different companies' modules. One of the things that I like about this one, and it's really interesting, is it's a single stage converter. So it takes 48 volts at the input. I think it's an LLC converter, though the details are secret. And it comes out in a single stage at 0.8 volts. So it's very efficient. It includes the computers in every one of those modules. So it's PM bus programmable, AV bus programmable.
So we're talking about the modules are all over
these
here?
are the modules.
Okay, let's zoom in on that.
And so we have 10 modules here. Each one of them is capable of 200 amps. And those all feed into what looks like that ASIC in the center. And that's what we're doing. We're doing the ASIC emulation. We designed the power supply, but we don't sell power supplies. We're building that ASIC emulator in the middle. And there's a total of 512 gallium nitride, what we call load cells. They're all identical load cells. And those come out through a digital bus controller. They're all time matched with meander lines and fan out drivers. They all come out to this 12-bit control line. That control line decides which of the switches to turn on when. And that comes down to a microcontroller. We designed that also. And I don't know if you can see that, but that's a microchip. DSPIC 33C, which right now is the fastest processor. And we're spitting out data at about 66 megasamples per second at 11 bits, which allows us to control that load all the way from 0 to 2047 amps at a 1 amp resolution. The question was really, what is this for? In the beginning when we were designing it, we thought this was about measuring load step response of power supplies at a faster rate than most people can. We're doing roughly 1,000 amps per nanosecond, which is kind of crazy. But we
1,000 amps per nanosecond.
1,000 amps per nanosecond. We thought that this was really about doing load steps. And one thing we learned, as soon as we introduced this at the Supercomputer Conference in September, people started to come talk to us about it. It's been a really popular display. And what they said is it's not really about power delivery per se at all. They're going to design the board now, but they don't have an ASIC for a year or two. And the concern is at these speeds, in such a small package, what happens with, what does the EMI look like in the package? There's a lot of power domains. What about power rail to power rail cross coupling, crosstalk? How does that work? And a lot of these chips, they have a tremendous number of Ethernet, data lines, signal lines, PCIe lines. How does this 2,000 amp signal get coupled into their signal lines? I had a boss 40 years ago, and he said, power supplies don't make money, signals do. So all of the money makers in that chip are the signal lines, not the power supply. And so what these companies are worried about is how do they predict how good those signal lines are going to be and whether they're going to get distorted a year or 2 years before they get the chip. And that's what this is all about. We thought it was bleeding edge. We have 2,000 amps in a 100 millimeter socket. Very first customer that came to see it asked if we could push that up to 6,000 amps. And a second customer that came said they have 2,000 amps, but it's in a 25 millimeter socket. Do we think we could shrink that? And I think that's kind of an indication of where the world is going. But I can actually run this for you live. It's actually running here.
Okay, let's see that.
So I have this running as a one-shot just so we can run it without cooling so you can see our load, but I push the button and we captured this waveform. The waveform is pre-programmed into the controller that we built, and this is really just for our demo purposes. But you can see we did some square waves, then we did some bursts, a few different waveforms. You can see the current in the yellow, and the scale is actually here on the right, so you can see we're hitting just about 2,000 amps now. And in the red, that's actually the voltage that we're measuring on test points on a circuit board, so we can see the voltage. But if I zoom in on this a little bit, you can see that we're actually running quite fast, and that allows us to synthesize almost any waveform that we want. So here we have a synthesized exponential rise time, and we can tell the controller what we want the time constant of that rise and fall time to be. And if you didn't like exponentials, well, there's a linear rise and fall, so we can do linear also. And if you wanted to measure FFTs, we can do sine waves. We can do 2,000 amp sine waves up to about 10 megahertz with this load, with a good display. In fact, here's a couple of different sine wave frequencies. And then maybe you just want to see a burst. If we knew where the resonance was in the power board, we might pick this frequency to match it. We just did a 33 megahertz burst so we could see what that would look like.
Steve, how do you measure 2,000 amps on the oscilloscope? How are you getting that?
So what we're actually looking at isn't the current signal, we're looking at the current programming signal. So we test individual cells using DC measurement, but at the high speed, there isn't a current probe that'll measure 1,000 amps per nanosecond, a bandwidth that's more than 350 megahertz. And if you look at the way the board is distributed, the current flows from every side. There isn't any single point on the board that contains the 2,000 amps. So this yellow trace is actually a measure of the current programming signal. That's the control voltage. If we want to actually measure the current, there's a few ways we do it, but one of them is to use near field extraction. We measure the near field in the load cell. We integrate that in the scope, and we get a picture of it. I have an article about it called How Fast is GaN Fast, and I actually showed that measurement. I also have a 2015 IEEE article that shows how we do that. Langery MV is probably the leader in that business, and they make very fine resolution current probes that use near field extraction to measure the currents. We did another trick that's kind of interesting in this board, and that is we're actually using vias as air core transformers. So we have the load cell, and the load cell connects to the decoupling cap on the back side of the board, and that connects through vias. So right next to that ground via, we put another via that's not connected to anything. We just bring that out to test points. And then we can actually measure the current in the via very accurately and up to gigahertz frequencies. We integrate that in the oscilloscope, and we get a pretty good picture of that. That's the way we can do it. It's not DC. That's, we can only see the edge. It's an AC coupled signal. The DC signal is a little easier to measure. We can measure the average current of that in the scope. Just takes the average envelope. We take the average input power. We know about what the efficiency of the converter is, and then we can pretty accurately correlate the current. But this is kind of where the state of the art is, and AI data center is really driving it to crazy levels. They look at what we're doing and they say it's crazy, and I said, we're not doing the crazy stuff. The data center and AI guys are doing the crazy stuff. We're just moving stuff out of the way so they can see it. But this is what we do, and we're having fun doing it, and we hope that it's everything that our customers need it to be.
Okay, Steve, thank you very much.